Reservoir sampling is the problem of picking a random sample from a stream. You are given K, the desired sample size, the caller decides how many items they want. You see items one at a time and you do not know how many there are. You can only keep K items in memory. We choose uniformly at random from the positions in the stream, each position has the same probability of being chosen. So if a value appears more than once, it has proportionally higher probability. We are choosing one position uniformly from the stream. In the first example with A, B, C, each of the three positions has probability 1/3. After the first item A, the reservoir holds A. When B arrives, we replace with probability 1/2, so the first and second position are equally likely. When C arrives, we replace with probability 1/3, so in the end the first, second, and third position each have probability 1/3. If the stream were A, B, C, each of the four positions would have probability 1/4, so the value A would have probability 1/2 and B and C would each have probability 1/4. We keep a reservoir of K slots. The first K items from the stream fill the reservoir. For each new item that arrives, we decide whether to include it. With probability K/I+1 we replace a randomly chosen slot in the reservoir with this new item, otherwise we leave the reservoir unchanged. After processing n items, each position has probability K/n of being in the reservoir, so the reservoir is a uniform random sample. We store the reservoir in an array or list of K slots, indexed 0 to K-1, so we can pick a random index and overwrite that slot. Fill the reservoir with the first K items. For each new item after that, with probability K over the number of items we have seen so far, we replace a randomly chosen slot in the reservoir with this item. This rule keeps the sample fair so that every position has the same chance of being chosen. To implement, generate a random float between 0 and 1. If it is less than K/I+1, pick a random slot and overwrite it with the new item. The old item in that slot is discarded and we do not keep it anywhere. When K=1 we only have one slot, we replace it with the new item with probability 1/I+1. No probability math is required beyond that. Item 1 is A. We fill the first slot of the reservoir with A. Item 2 is B. We fill the second slot. Now the reservoir has A and B. We get C. We generate a random number, suppose we get 0.5. 0.5 is less than 2/3, so we include C. We pick a random slot from 0 to 1, suppose we get J=0. We overwrite slot 0 with C, reservoir is now C, B. We get D. We generate a random number, suppose we get 0.6. 0.6 is greater than 2/4, so we do not include D. The reservoir stays C, B. We get E. We generate a random number, suppose we get 0.35. 0.35 is less than 2/5, so we include E. We pick a random slot, suppose we get J=1. We overwrite slot 1 with E, reservoir is now C, E. We get F. We generate a random number, suppose we get 0.9. 0.9 is greater than 2/6, so we do not include F. The reservoir stays C, E. In the end, Each of the 6 positions had probability 2/6, or 1/3, of being in the reservoir. With k equals 2 we keep 2 slots and pick a random slot whenever we decide to replace. Edge cases. If the stream has fewer than k items, we take all of them, the reservoir is just the whole stream. If k is 0, we return an empty sample. If the stream is empty, we also return an empty sample. Time is O of n, we make one pass over the stream, and for each item we do constant work, generate a random number and maybe overwrite one slot in the reservoir. Space is O of k, we only keep the reservoir of size k. We define reservoir sample of stream in k. We create an array of size k and fill it with the first k items from the stream. Then we set I to k, and while the stream has more items we get the next item. If a random number is less than k over I plus 1 we pick a random slot j from 0 to k minus 1 and overwrite reservoir of j with the item. We increment I and repeat. Finally we return the reservoir.